How's it going, everyone? Welcome to the second drill. Today we're going to be talking about dichotomous predictors when we just have two groups, and so this will end up being equivalent to t-test or NOVA with a dichotomous predictor, as we'll see towards the end of this lesson. I've already actually run these first couple libraries because I just want to dive right in. And you'll notice that I have three things already in my environment. Those are some plots that I'm going to show later that I don't have the code for the plots in the script itself, but I got some visualizations that I want to discuss. So that's why I've already run some stuff and I have some stuff in my environment that you won't have, and later on in the script you'll see those again. And I have a note in there saying that if you try to enter P01, it's not going to work because you don't have that actual plot generated. But anyway, so today we're going to look at a a data frame that looks at grades 3 through 8. It has four variables, basically four measures. Some assessment of math accuracy. So they have three tasks: some sort of addition task, some sort of subtraction task, and some sort of multiplication task. And then the ACC mean is the overall accuracy. So if you just average across all three of those different tasks, overall, how accurate were they? So basically, our ACC mean, our dependent variable in this data set, is essentially a measure of some form of math abilities, you might call it. It's broken down again by grades 3 through 8. And the only other variable is that male and female. So that's what we're going to be focusing on today. Is we're going to be looking at gender differences in this math accuracy. So when it comes to encoding two groups, really there are literally an infinite number of ways that you can code it. Some ways make the interpretations of the coefficients meaningful, and some would be nonsense. The most usual ways that you'll see are 0 and 1, negative half and positive half, and sometimes you'll see negative 1, positive 1. So those are the three ways that we're going to look at today. You might sometimes hear these referred to as dummy coding for 0 and 1. Typically, if somebody says something is dummy coded, they're coded as zeros and ones. There are different names. Don't get wrapped around any of these particular names because different people use different names for different things. But I've often heard like the negative half, positive half referred to as a contrast code as opposed to a dummy code. And then the negative 1, positive 1, I've heard referred to as effects coding. And we'll talk about, this whole drill is really about the differences in these three different approaches. But we're also going to take a quick peek at R's default behavior so that you know how to handle that. So the first thing that I want to do is we're going to create four new variables. One called gender.factor, and it's literally just taking our gender, because you notice that gender is not actually a factor, it's a character vector. So right now, gender is not a factor, it is just a bunch of characters. So we're just going to use as.factor to take that gender variable right here, and we're going to create a factor and let R do its default thing and how it treats that factor. Then we're going to create three separate gender variables. One, that we're using this if-else statement, and we're saying that if the gender is male, code it as 0, otherwise code it as 1. For gender .5.5, that's just my notation for saying, hey, this is the negative half, positive half coding, where if gender is male, code it as negative half. If not, code it as positive half. And then for gender 1.1, that is the negative 1, positive 1 coding, where if gender is male, code that as negative 1, and code females as positive 1. So once we run this line, we now have, if we look back at our data frame, you can see that we now have these four additional variables. Only now gender factor is an actual factor, as opposed to the original gender variable is still a character. And so if we just look at those variables that we've created now, the original gender, again, it's character, but now gender.factor is actually a factor. We have gender 0, 1, where the females are coded as 1s here, and gender 5, 5, females are coded as positive half, males are coded as negative half. And then on the gender 1.1, females are coded as positive 1, males are coded as negative 1. So everything looks all great and grand here, right? Well, no, not really. If we look at the levels of the factor, where we just allowed R to do its default thing, and we just said, hey, make this a factor and do with it what you will. If you look at the levels in that factor, it's female and male, or if you use the contrasts function, this will show you how all the contrasts are coded. And in this case, it has female coded as 0 and males coded as 1. So when R coerces some character vector to a factor, it by default orders, it takes all of the unique occurrences in that character vector, which in this case the only unique occurrences are female and male, so it knows that it only has 2 levels, but it orders them in alphabetical order. So that's the order that it gives them in. So if we, where we decided to code males as 0 and females as 1 in our dummy coded version, R coded females as 1, males as, females as 0s and males as 1s, because female comes before male alphabetically. So that's important to know, and we'll see how that flips our effect here in a bit. But it's always important to pay attention to whenever you do things like, just wrapping something in as factor, for instance, and what does R do with that under the hood? Because if, for instance, we coded male as 0, female as 1, and then when you were plotting, you decided to color it by gender, and so you just put color as your gender. Well, since it's a continuous number, it's going to be it may tell you, or it may give you that gradient instead of like red and blue. It'll give you, dark blue to light blue as that default, fade color kind of thing. If you wrap it in just as factor, now all of a sudden it codes females as 0 and males as 1. So you may, on your plot, literally reverse your colors there. So just be aware of what's going on with the default stuff. And that's why I personally advocate, I always explicitly do my own, and I always have both factor and numeric versions of all of my different variables, so that I have a very concrete, like I can look and see like, okay, females are coded as 1 or females are coded as 0.5, and not really just defaulting to having the labels. I could talk more later or in drill about why I strongly prefer creating my own labels. But if you want to discuss that, then come see me in drill. Anyway, so point is that we can see here that whenever we use just that default R's default behavior, it coded females as 0, males as 1. That's the opposite of what we're doing, so go ahead and just wipe this out of your mind, and we're just going to focus on this gender 0, 1, 5, 5, and 1, 1 that we created, and these are the 3 that we're going to be mostly looking at. So first, let's summarize some data, and say we want to see like, well, what is the overall math accuracy by gender among, say, 3rd graders. So, all we got to do is we start with our data frame, we pipe that into a filter, and we're going to filter to where the grade equals 3, so that we only get 3rd graders. If we just run those 2 lines, then we can see like, okay, well, that gets us down to 28 3rd graders. Pipe that into group it by gender, and at this point, like if you just run those 3 lines, like everything else turns out the same. Like it looks identical to this because it hasn't actually done anything with those groups, except it does at least acknowledge here that it is grouped by gender and that there are 2 levels of that grouping variable, whereas before there was no grouping variable. So now that we've grouped it, all we got to do is tell it to summarize, and we'll tell it to give us some variable called m, and that's the mean of ACC mean. And so when we run this line, we have the our means for females and males here. Now I kind of paused there for a second because I realized that after running it earlier, I didn't reset the default options. If you're running this line right now, you probably see 83.8 and 87.6 instead of these 2 digits, and that's because Tibble defaults to 3 significant digits. And notice that I say it's significant digits, not like a specific number of decimal places. If your 3 significant digits has no decimal places, like Tibble will actually cut off the decimal places altogether, which is why you couldn't even use round on this, because if you round it, it'll still round it to say 2 decimal places, but then Tibble only displays 3 significant digits. So if you really want to change that, you can run option pillar.sigfig equals, say, 4, which is what I had done previously, which is why when I ran this, it showed up as 4 significant digits instead of 3. And like, I rarely need the console itself to display, like, just keep in mind that literally just applies to how the console is displaying, and it's not actually cutting off those numbers. So I just usually leave it at its default. I don't care. It doesn't really bother me that much, at least not enough to change options every time I open up a script. And under the hood, even if it only displays 83.8, it still knows the full numbers. And if you were to export this Tibble into, say, a CSV and open it up in Excel, this would give you the full number. So the number is still there if you need the full number. It just defaults to 3 significant digits to try to keep the console as decluttered as possible. Or like, if you really want to see if you have 83.8 and you don't want to bother with having to remember the pillar sigfig and change the actual options for the whole thing, you just want to see more digits on this one particular table, you could always just take that and pipe it into a data frame, and when you do the data frame, it will give you more decimal places. So just FYI, that's how you can look at how you can see more decimal places. But either way, we can see here that it seems that 3rd grade boys on average are about 3.76 points higher on the overall accuracy mean than girls. So real quick, let's just take a quick look at a plot where we can see what these look like. So this is all of our 3rd graders with our males over here and females over here. Here I just have a note that where I use geom jitter so that I could allow the points to jitter to the left and right a little bit. They're allowed to move 0.2 just so that they're not all stacked up on each other. But I said height equals 0, meaning that it's not allowed to jitter up and down, so that there's fidelity of the y-axis, but the left-right, it's allowed to jitter, since we know that this whole group over here is females, and it doesn't need to be directly on that center line. So anyway, here's the points that we're looking at, and we see that like the females, the average is 83.84, and then for males, the average would be 87.6, so somewhere around in here. So getting into our models, like I said, we can see based on just our group means that 3rd grade boys scored approximately 3.76 points higher than 3rd grade girls on average. So let's model it to see if this difference is significant. So here I'm going to create 4 models: mod factor, mod 01, mod 55, and mod 11. Where for mod factor, all we're doing is for each one, we're going to take our data frame, we're going to filter to just the 3rd graders, and then pipe that into our LM. And for our formula, we're just going to do ACC mean, that overall accuracy mean, regressed on, in this case, gender factor to make mod.factor. The second model, mod 01, is the overall accuracy mean regressed on gender coded as 0 and 1. Mod 5.5 is the same. It is that overall mean regressed on gender coded as negative half and positive half. And mod 1.1 is that overall mean regressed on gender coded as -1 and +1. So let's first look at how that default factor versus the dummy coding that we created. Because again, I showed you how by default R uses alphabetical order, but in our case we didn't. So when we run it this way, this should say how these slopes. When we run it this way, notice how these slopes are the same except for that sign is flipped. And then when you look at our intercepts, those are different as well. So why is that? If we look and we see that here, the estimate is, or that intercept on the default coding is 83.8, and the intercept on the our 01 coding is 87.6. So do those numbers sound familiar at all to you? Because they should. If we go back up and look at our group means, we can see that those are the group means. So in other words, this default coding, our intercept is the mean of females, and our slope is how much that changes by changing from females to males. So this slope here, our intercept is the average where x equals 0, which in this model 0 equals female, because that was the alphabetically it came first. So in other words, this is the average of females, and then changing from 0 to 1, a 1 unit increase in gender, which means switching from female equals 0 to male equals 1, is associated with a 3.76 point increase in y. By contrast, over in the model that we created, where we coded males as 0, now the intercept again is the average where x equals 0, well, x equals 0 for males, and then a 1 unit increase on gender from male equals 0 to female equals 1 is associated with a drop in 3.76 points. So that's what I meant when I say it flips this effect, and you got to be careful about when you're coding these things, because it could be rather embarrassing to write up a manuscript, you send it off for review, and then you end up having some reviewer catch the fact that you say blah blah blah, the slope of gender is significant, because you just run it as this default factor, and you say, you know, the slope is significant such that on average third grade females score 3.76 higher than third grade boys. But then when you look at your plot, you overlook the fact that, wait, that doesn't line up with what the data look like, and oh shoot, that just flipped around the thing, and you're literally interpreting it backwards. And that kind of thing happens. You have to be careful about being conscious of how your data are coded, and thinking about and verifying what is coded as 0 anytime you're running these models, just to make sure that you're not flipping around effects and such. I personally never use factors whenever I'm doing a regression. I always use these, like the manually coded things, regardless of whether I'm using 0, 1, or negative half and positive half, which is, it just depends on what I'm going for in my interpretation. I will say that I almost never, in fact, I personally do never use -1 and +1. We'll talk about why here in just a second. But first, so here's like the 3 plots that I'm going to run as we talk about these models. And so hoping that we can, by visualizing it, start to understand really intuitively what these regression tables are telling us. So the way I have this, again, P is just a plot, and again, if you run these lines, nothing's going to happen because you don't have these plots. I ran these plots separately. But P01 is, it coded as 0 and 1. P55 is negative half, positive half, and P11 is coded as positive 1 and negative 1. So I'm going to open this up so we can see our plots here, and we'll look at each of these three plots. So here's the first one. This is with males coded as 0 and females coded as 1. And all I've done is I've set the background to where the plot will be the same, and the only thing that moves around is the data based on how it's coded. So when we look at our model summary for the model that's coded 0 and 1, we know that males are coded 0, females are coded 1. So what is this intercept? This intercept, 87.6, is the average for males, because it is the average where x equals 0, which in this model, x equals 0 at males. The slope is how much that average is predicted to change with a 1 unit increase in gender. Well, what is a 1 unit increase in gender? Male is 0 and female is 1, so a 1 unit increase in gender means 4 females. So the way you can interpret this, and what this looks like over here, is these red dots and error bands are the means and confidence intervals for the two groups. So our intercept, 87.604, is this green dot right here. So you can see it's where our regression line crosses at x equals 0, which happens to be exactly at the middle of the males, because we have males coded as 0. Then this minus 3.76, that's telling us that going from 0 to 1 drops down 3.76 points. So in other words, this red dot here, that is 1 unit above 0, is 3.76 points lower. So now if we look at that coded as negative half and positive half, the only difference is we're now shifting from, instead of it being at 0 and 1, it's now at negative half and positive half. But notice how that slope, that blue line, doesn't change. And when we look at our summaries, we can see that that's exactly what it shows. Here on gender 5.5, our slope is negative 3.76, same as gender 0.1. So looking between these two, we see that doesn't change our slope any, just like we've done before. It's kind of like recentering your data, and all you're doing, which means that it does, notice, shift that intercept. That here, our intercept is 85.72. It's no longer 87.60. So now what that means is, because when we look at our summary table here for our model coded as negative half and positive half, our intercept is still the mean where x equals 0. But notice where x equals 0, that it's no longer males. Like the group male is no longer at 0. So 85.72 is no longer the mean of a specific group, but rather it's, exactly halfway between the two groups. So what does that mean interpretively? That means that 85.72 is actually the mean of group means. So if you take this red dot here and this red dot here and take the mean of those two values, that mean will be 85.72. So when you're coded as negative half and positive half instead of 0 and 1, your intercept is the mean of group means instead of the mean of whichever group is coded 0. And your slope is still interpreted as a 1 unit increase is predicted to increase or decrease y by such and such amount. In this case, we're saying a 1 unit increase decreases the predicted value by 3.76 points, because it is still a 1 unit increase from negative half to positive half. It drops down that exact same 3.76 points. The only difference again is here 87.6 is the average of the people who are coded as 0, And here, 85.72 is the average in between these averages. It is the average of averages because it is that point directly between those two groups. So then what about our final model here? What about when we code this as -1 and +1? Now we notice that when we compare that to our -half, +half, our intercept stays the same, 85.72, but now our slope has changed. Why is that? Well, let's look at what it looks like to graph this as -1 and +1. So again, here is the same thing. We're just shifting out to -1 and +1 instead of -half and +half. So you notice that green dot, that spot directly between the two groups, hasn't changed. It doesn't matter what you code this. If you coded females as +1 billion and males as -1 billion, the exact halfway point between the two would still be 85.72. So the intercept doesn't change here between these two, but our slope does. And why is that? That's because if you notice, we no longer have a 1 unit increase between this group and this group. Rather, it's a 2 unit increase. So 1 unit from the center of the males to the mean of group means. And there's 1 unit between the center of females and the mean of group means. So in other words, instead of this slope being interpreted as a 1 unit increase, or rather it is interpreted as a 1 unit increase in X is associated with blank amount of change in Y, in this case 1.88 points. But because 1 unit is not the difference between groups anymore, 1 unit is the difference between the group and the mean of group means. Now, the way that this is interpreted is our intercept, 85.72, is the overall average. It is the mean of females and males combined, the mean of group means. And our slope, gender 1, is the average difference for each group between that group's mean and that overall mean of group means. So in other words, whereas this slope, when it's coded as -half and +half, this slope tells us the difference between groups. When it's coded as -1 and +1, instead of telling us the difference between groups, it tells us the difference between the group and the overall mean of group means. I personally have never in any research context found this to be helpful, and I don't really often see dichotomous groups coded as -1 and 1 because it makes more sense to only code them as one group apart. Typically, when you're looking at groups, you're more interested in the difference between the groups rather than the groups from the grand mean. And so interpretively, this one makes a lot more sense to me. In fact, I even double checked with Bill to ask him just to make sure that I wasn't overstating it and that there wasn't some technical reason that like, oh well, it also, when you code it as -1 and 1, it does this, blah blah blah. And essentially he said like, yeah, no, we're briefly covering it because they also mention it in the book, but like there's nothing special about it other than the slope tells you the difference between the mean of group means and each group instead of the differences between the groups themselves. So anyway, point is that if we look at all three of these plots together, what we can see again is that here it's coded as 0 and 1, here it's -half, +half, and here it is -1 and 1. So we can see that as long as we're keeping our groups 1 unit apart, it's not going to change that slope. Our slope is always going to be that difference between groups. But then as we start changing from -half to -half, +half to -1 and 1, now it does change our slope, but it doesn't change our intercept because that intercept is still the point between the two group means. I have a video on the YouTube channel where I discuss it's called it's called sidebar. Why the grand mean or mean of group means is not always equal to grand mean or something, because you may hear people calling this the grand mean. And long story short, that's only technically true if it's a perfectly balanced design, if you have 14 males and 14 females. But if you have 15 females and 14 males, then technically that becomes a biased estimate as the mean of, and it's more appropriate to call it the mean of group means rather than the grand mean, because if you actually take the grand mean, meaning you just take the full mean of all of these points, that'll be slightly different than if you take the mean of females and the mean of males and take the mean of those two values if you have an unbalanced design. So I have a video that visually explains why that is. If you want to see it, you can look for that in one of the playlists and check that out. So the last thing that we're going to do is we're going to look at this at how, like if we wanted to do this as like a t-test or an ANOVA, which is kind of weird with the dichotomous predictor, but mathematically the same, we could do that. We just take our data frame and we're still going to filter it down to only third graders and pipe that straight into the t-test function and tell it that our data equals period, that placeholder, so that the t-test function knows, hey, take this pipe and put it in as our data. And then the t-test function will tell it, that ACC mean regressed on gender. And then we're going to put in this argument var equals true because it defaults to false. And this is just asking whether or not to treat it as equal variance, and that where it's true, which is what we want here, it uses pooled variance to estimate that variance. Otherwise, it uses some approximation. And so if you ever run these things and you see degrees of freedom that's some weird like decimal place, then that's because you have var equals false. But anyway, so if we run this, we get our t-test. Like this is the standard, run-of-the-mill t-test. And what we see is that we can say t equals negative 1.14 on 26 degrees of freedom, p equals 0.26, and our 95% confidence interval of the difference between the two groups is negative 10.52 to 3.00. And this also gives us those mean differences, so the males and females. So because this 95% confidence interval of the difference captures 0, that means that it's not going to be significant. You don't even need this p-value if you have this 95% confidence interval. If this 95% confidence interval was 0.0001 to 3.00, then this p would be less than 0.05. If your confidence interval does not capture 0, then you are saying you are 95% confident that the true population parameter is not 0, is not within the bounds of the true population parameter. In other words, the difference is not 0. But here, the difference very well could be 0, and that's why this is not significant. The other way would be if we could do this as an ANOVA. So same thing, just filtering down to third graders, plugging that into the AOV, the ANOVA function. Same thing, data is the placeholder, this pipe coming in. ACC mean regressed on gender, and then pipe that into our summary function. And we can get this reported as an ANOVA. And, I just want to point out here that you'll notice that our t here of negative 1.426, if we square that, that gives us 1.305, which is the f value, and our p here again 0.264, and then up here 0.264. So this is telling us, this is giving us the exact same information. It's just giving it as an ANOVA table instead of as a t-test. So the point is that anytime you hear somebody talking about ANOVAs or t-tests, you should know that those are just general linear models. They are special cases of a general linear model. A independent sample t-test specifically is a general linear model that has two parameters, the intercept and a dichotomous predictor. Like that is an independent samples t-test. And same thing here with this ANOVA. Like, it really is the same thing. That's just a different way of representing it. But the point is that these are not like approximations. They are mathematically the same. I have a whole like hour-long farm talk that I gave. That's another video where I kind of run through showing how these things are the same. So anytime anybody starts talking t-test, just think, general linear model with a dichotomous predictor. That is a t-test. That is what you're doing. You are looking at what is the slope of this blue line, because that is the difference between groups on average. And is the slope of that significantly different from 0? When we going back to looking at our model summaries, I just want to remind you as a final thing here that what this is testing here, this t-test, and this p-value, 0.264, this is just like everything else that we did. This is saying if we just do p55 plus geom h line, oops, nope, sorry, that should be 85.72. So here then, what this is testing, if we just have one line that is the intercept only, which is this black line right here, what is our sum of squared errors of using this black line? So we predict this value right here for all of the females, and this value right here for all of the males. Well, you can see, like, on average, we'd be under predicting male scores and we'd be over predicting female scores. So instead, if we use this blue line so that we predict this red dot for all the males and this red dot for all the females, what is the sum of squared errors for using this blue line instead? And does the sum of squared errors decrease significantly given one additional parameter by including that parameter? That's what this P and T right here is testing. It is asking, if we include this blue line as our predictor, does it significantly reduce error beyond 0? And the answer is no. Like in this particular case, it does not. So there is not a significant effect of gender, at least not in 3rd grade, or so it seems. So that is, I guess that wraps up the bulk of today's lessons. If you have any questions, let me know, and we can discuss more in drill this coming week.